A 600 turn solenoid is 0.55 meters long and 4.2 centimeters in diameter. Inside the solenoid, a small 1.1 centimeter by 1.4 centimeter single turn rectangular coil is fixed in place with its face perpendicular to the long axis of the solenoid. What is the mutual inductance of the system? Okay. So here's an end view of this. So here's the solenoid and there's the rectangle. Okay. So the magnetic field, what we'll do is, so we'll make the current flow in this direction, and the magnetic field is coming out of the plane of the paper. And as the current increases, the magnetic field will increase, the flux through this will increase, and using Faraday's laws, we can calculate the induced EMF. If the flux is increasing coming out of the paper, the induced current will have to be in the opposite direction. So let's write induced EMF will be, we'll do induced current. Okay, anyway. So let's start with Faraday's law. Faraday's law says induced EMF equal to minus d phi by dt. Okay. And we already have the direction of the induced EMF, so we'll just calculate the magnitude now. So induced EMF equal to d by dt, and the flux through that rectangular loop is B times area equal to, and B for a solenoid, the magnetic field inside the solenoid is given by mu naught n I. Okay. Okay, so the induced EMF is d by dt of mu naught n I area, and that's equal to, and we're going to change the current, so mu naught n area di by dt. Okay, so this is the induced EMF from Faraday's law, from this Faraday's law. Now you compare that to the induced EMF in the second coil, in the rectangular coil, due to change in current in the solenoid. This will be the mutual inductance. So the mutual inductance is mu naught, and remember we had dropped the sign on this one. All right, actually, so we'll keep the sign back. So the mutual inductance is N area. Again, this is N is the number of turns per unit length in the solenoid. A is the area of the rectangular coil. So that's the mutual inductance. Okay.